Hello, today we are going to learn sequences. Let's learn what are the sequences. First, I'm going to give you this example. Let's consider you have this set of numbers 1, 2, 3, and then you have this set of numbers 1, comma, half, comma, 1/3. These are not just a set of numbers. These are actually having some pattern. Okay, having some pattern. For the first set, the difference between two consecutive numbers is 1. In the next case, the pattern is always you divide 1 by the set given in the first point. All right. So the first point is the first point. The numbers are given like 1, 2, 3. In the second point, always you divide 1 by the number given in the first point. So both are considered to be sequences because they are having patterns or maybe order, proper order. All right. So let me write. So this is sequence 1. This is sequence 2. Okay, let's learn the definition of a sequence now. Definition: a list of numbers in a special order A1, A2, AN and is called a sequence. Okay, they should be in a special order. There should be pattern. There should be pattern between numbers. All right, so that's called a sequence. All right, then let's learn the short notation. Before learning short notation, let's learn about this term. This is called the end term. You know that. This is called the end term of the sequence. Now we're going to learn the short notation. The short notation is AN. N goes from 1 to infinity. Okay, that's how you write a sequence. Okay, so you just put these curly brackets, and in the right hand side curly brackets you have to mention the start and the end. It says n goes from 1 to infinity. That means it is starting from n equals 1 and it has infinitely many terms. All right, so that's how you write a sequence in a general format. All right. Thus, now we have to put the two above sequence into the general format. Let's say this is given to you 1, 2, 3, ... And the format of this one is actually n to the power, n curly brackets, and then you have to write n goes from 1 to infinity. Okay, so this is the end term. You can understand in this series, in this sequence, end term is just n. Let me write the end term too. 1, 2, 3, ... n ... Okay, so this is the end term. And then let's consider the next series. 1, 1/2, 1/3, ... N term is actually 1/n ... Okay, so if you write the general notation, the short notation of this one, it is actually 1 over n. N goes from 1 to infinity. Alright, so these are the two short notations. And then let's move to the next definition, where we learn convergence and divergence of a sequence. Definition: if limit n goes to infinity, an equals infinity, then we call an is divergent. Give me a second. Okay, that's how we define the divergence. And then we write the convergence if limit n goes to infinity, an does not equal to infinity, then we call n goes from 1 to infinity, an is convergent. Okay, so this is how you define convergent and divergence. If this happens, you say it is divergent. If that happens, you say it is convergent. Okay, you have to just check the limit of the n term when n goes to infinity. Okay, now we are going to reconsider example number 1. Now just write the first sequence, which is 1, 2, 3, dot, dot, dot. That is the n term. Now find the limit of the n term where n goes to infinity, which is just infinity. Then that means this series diverges. Alright, the series diverges. I'm sorry, I said this sequence, not series. This sequence diverges. Alright, in the next case, let me just take these here a little bit. Alright, good. Then the next example, where here we have 1 over 2, 1 over 3, dot, 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 1 over n, dot, dot, dot. Now take the limit of the series when n goes to infinity, which is 0. This means the sequence converges. Alright, so it does not equal to infinity. What I got was 0. The limit is 0. That means it does not equal to infinity. Alright, so it is convergent. Okay, you had two examples, one example for convergence, the other example for divergence. Alright, now let's move to the next part. Now I'm giving you some important information, so I use these pointers to explain them. Pointer 1, All right, so what I'm saying is we need to find the limit of a sequence in order to find it is convergent or divergent. All right, that's you understood already. We have to find the limits before talking about convergence or divergence. In the next pointer, then the question is how to find limit of a sequence. All right, how to find the limit of a sequence. How to find the limit. There are several ways of finding the limit of a sequence. There are three main ways that we're going to learn in this class. Just go one by one. The first approach is applying rules of the limit. Okay, applying rules of the limit. Okay, so this is the question we had. All right, so the first case is applying rules of the limit. Now let's learn this. So there are three main rules that I'm going to write. First rule is sum or difference rule. You have learned this in Calc 1. Today I'm going to give you a quick review. Sum or difference of sum or difference rule. Okay, so that is, let's say you are given limit n goes to infinity an plus or minus bn. If you have a sequence like this, then you can get the limit separately. That means you can write limit n goes to infinity an plus or minus limit n goes to infinity bn. Okay, you can get the limit separately. That's part A. Part B is constant multiple rule. Multiple rule. That means, let's say you have something like this. Limit n goes to infinity and you have c times an. That means an is multiplied with a constant which is c. So what you can do is you can get the c out from the limit and get the limit of the an individually. All right, then go to C, product rule. Limit n goes to infinity an times bn. This equals limit n goes to infinity an times limit n goes to infinity bn. That means you can get the limit separately. You can get the limit of an and bn separately and then multiply them. All right, so D, the last rule, quotient rule. All right, quotient rule is also similar to the above rules. So let's say limit n goes to infinity, Let's say you have an divided by bn. Now you get the limit of an separately and then divide that by limit of bn. Alright, so these are the rules, 4 different rules that you learn in Calc 1. I'm just giving you a review in this class. Alright, so you could use any rule you would like in first approach. The first approach is applying rules to find the limit of a sequence. Alright, so that's the first approach. Now let's learn a new example. This is example number 2. Find the limit of n over n plus 1. N goes from 1 to infinity. You have to find this converges or diverges. Let me write like this. Find this series is convergent is what's going on? Give me a second, sorry. Okay, you have to find this convergent or divergent. For that you have to get the limits. That's the first part. You write limit n goes to infinity, you find the limit of that. Alright, if you apply the limit right here, what you get is, let me write it in green, what you get here is infinity over infinity. Okay, so this does not exist. So you can't just apply the limit. Now, because of that reason, you have to use your knowledge from Calc 1 where you learn limit of function. Here, the simplest thing that you could do is you could divide the numerator and denominator by n. Okay, so what I'm going to do is I'm going to divide numerator by n and denominator by n. Right, so let's see what I get. Limit n goes to infinity. I get 1 in the numerator and I get 1 over 1 plus 1 over n in the denominator. Okay, let me rewrite this like that. Alright, now let's check whether you can apply the limit. If you apply the limit, what you get here is 1 over 1 plus 0, which is just 1. Okay, which is just 1. So then that means the limit exists. Okay, the limit exists. Limit does not equal to infinity. So your answer is it is convergent. That series convergent. Okay, that series is convergent. Alright, so let's move to the next example. Example number 3. Now you have 1 minus n to the power 3 over 70 minus 4n to the power 3 and n goes from 1 to infinity is convergent or divergent. Alright, so same thing you have to do. You have to get the limit of the nth term. So I write limit n goes to infinity, 1 minus n to the power 3, 70 minus 4n to the power 3. Alright, first apply the limit and see whether you can get something other than an indeterminate form. It is infinity over infinity, which is indeterminate. Okay, rather writing does not exist, let me write down like indeterminate. This is indeterminate. Let me clean that. What I want to say is it's indeterminate. So here also this is indeterminate. Alright, because it's indeterminate, you have to use rules of limit. First of all, to avoid this indetermination, you have to divide numerator and denominator by highest power of n, which is n to the power 3. I write this to be limit n goes to infinity, and I write 1 over n to the power 3 over n to the power 3. Here I write 70 minus 4n to the power 3 divided by n to the power 3. Okay, then you write limit n goes to infinity. For this one you write 1 over n to the power 3 minus 1. And here you write 70 over n to the power 3 minus 4. Okay, now you're going to apply the limit. If you apply the limit, this will be, you can bring a limit. You can bring this limit to that part and this part separately. So you write limit n goes to infinity, 1 over n to the power 3 minus 1. And here you write limit n goes to infinity, 70 over n to the power 3 minus 4. Alright, this equals, the limit of that one should be 0 and that one also 0. Okay, technically what I want to say is this is something like 1 over infinity, which is 0. This is also 70 over infinity, which is 0. So the answer should be 1/4. Alright, so this is divergent. I'm sorry, this is convergent. Thus, why it is convergent? Because you got a real number, not infinity. If you had infinity here, then you could say it is divergent. In this case, it is convergent. Thus, the given series, which is limit n goes to infinity, 1 minus n to the power 3 over, I'm sorry, no, I'm talking about the series, not the limit part. 1 over n to the power, 1 minus n to the power 3 over 70 minus n to the 4n to the power 3 n goes from 1 to infinity is convergent. Okay, so this is the first case. This is the first case that we discussed right here. This is the first case, applying rules of limit. Okay, now we move to the second case. The second case is use Hopitals rule. Use Hopitals rule for the indeterminate forms. for the indeterminate forms. All right, let me explain how does this work. First of all, let me explain what are the indeterminate forms. There are 7 indeterminate forms. Let me write them. These are the indeterminate form. If you have something like infinity over infinity, that is indeterminate. If you have something like 0 over 0, that is indeterminate. And 0 times infinity is indeterminate. And then infinity minus infinity is indeterminate. 0 to the power 0 is indeterminate. 1 to the power infinity is indeterminate. Infinity to the power 0 is indeterminate. All these are indeterminate forms. All right. Now let's learn Hopitals Rule that you learned in Calc 1. That's all right. I'm going to give you a review about Hopitals Rule. So you write L Hopitals Rule. So this is the Hopitals Rule. If limit n goes to infinity, fn over gn is indeterminate, and limit n goes to infinity, f prime n over g prime n exist, then this limit n goes to infinity, f of n g of n is actually limit of the derivatives. All right, so that is Hopitals Rule. All right, so let's move to examples. Let's discuss example number 4. In example number 4, we're going to compute, what we're going to compute is this sequence ln n over n. N goes from 1 to infinity is convergent or divergent. Okay, you have to find this is convergent. Let me correct it. Convergent or divergent. Okay, you have to find this convergent or divergent. Now you have to use the Hopitals Rule. First of all, let's take the nth term n term is ln n over n. Whatever given here is the n term. Okay, that is the n term, which is an. Alright, so you got the n term and get the limit of the n term. Limit n goes to infinity an equals limit n goes to infinity ln n over n. Now if you apply the limit, I will put it in green. So what you get is when n goes to infinity, ln goes to infinity, and this n goes to infinity. So this is indeterminate. Alright, indeterminate. Because of that reason, we have to use the Hopitals rule. Okay, then use. Let me write like this. Since the limit is indeterminate, we have to use the Hopitals rule. Alright, so now I'm going to use the Hopitals rule. For that, I just get the derivative of the numerator and denominator. So what I write is limit n goes to infinity ln over n is this equals limit n goes to infinity, the derivative of the numerator and denominator. Derivative of the numerator is 1 over n. Derivative of the derivative of the numerator is 1 over n. The derivative of the denominator is just 1. Okay, it is just 1. So now you apply the limit and see whether it works. If you apply the limit now, it is 1 over infinity, which is 0. Okay, which is not an indeterminate form. Okay, that means it has a limit. Thus, since it has a limit, it has a real number limit, then you say it is convergent. ln n over n, n goes from 1 to infinity, is convergent. Alright, let's move to next example. You write n, the next example is this, n times e to the power negative n n goes from 1 to infinity. You have to find this is convergent or divergent. All right. Now the same thing, we have to use the Hopitals rule. First of all, let's get the n term, which is right here. And then get the limit of the n term, which is limit n goes to infinity, n e negative n. Now apply the limit. What you get here is, I will write it in green. You get 0 times when n goes to infinity, e to the power negative n is I'm sorry, I made a mistake here. So what I'm saying is when n goes to infinity, this term goes to infinity and that term goes to 0. Okay, it is infinity times 0, which is again indeterminate. Which is again indeterminate. All right. Now use the Hopitals rule. Okay, now we are going to use the Hopitals rule. Now, if you use the Hopitals rule, you get this. First of all, let me write the original equation, the limit. That's what we need. We're going to use the Hopitals rule for that. Before using Hopitals rule, you have to make this having a numerator and a denominator. Okay, this should have a numerator and denominator. For that, we could write this as limit n goes to infinity. This is n over e to the power n. All right, now this has numerator and denominator. That's the way Hopitals rule works. If you can go back to the place where we learn Hopitals rule, see, it should have a numerator and denominator. All right, so go back. So you write it as this. So this becomes that. And then you have to use the derivative. You write limit n goes to infinity. The derivative of n is just 1. The derivative of e to the power n is just e to the power n. Okay, those are the derivatives. Now you get the limits. That is 1 over e to the power infinity is just infinity. All right. Now you write 1 over infinity, which is 0. All right. Give me a second. All right. It is 0. So you could say the limit is 0. That means this sequence converges. All right. All right, go forward. I'm sorry, the sequence. The given sequence is this. N e to the power negative n. N goes from 1 to infinity. Is convergent. All right, we discussed 2 examples in this part. This is number 2. That is number 2, where we use the Hopitals rule. Now we move to number 3, where we use some other method. All right. Now go to the next approach, which is called the Squeeze Theorem. This is part 3. Use Squeeze Theorem. Let me explain what the Squeeze Theorem is. This is a very easy theorem, which is a Squeeze Theorem. If an greater than or equals bn greater than or equals cn for n greater than or equals n naught and limit n goes to infinity an equals limit n goes to infinity bn equals L. That means limit of this one is L and limit of that one is also L. Limits are equal. Alright. Then we could say limit n goes to infinity bn is also L. Okay, this is a very easy theorem. What this says is you have three sequences. You have three sequences. One sequence is in the middle, and the other two sequences are left and right. This says the limit of that one goes to L. The limit of that one goes to L. Then what about the limit of the middle one? It should also go to L. All right, I'm explaining it again. There are three sequences. Those three sequences are like this. One sequence is in the middle, and the other one is less than that, other one is greater than that. So you say the limit of that one goes to L, limit of this one goes to L, the limit of the middle one should also go to L. Okay, which is a very easy theorem. All right, let's go to examples. This is example number 6. You have to consider this sequence cos n over n. N goes from 1 to infinity. You have to check whether this converges or diverges. Alright. Now you have to make something like this. Okay, you have to set the given sequence at the middle, and then you have to make another two sequences left and right. Okay, I will explain how to do this. It's easy to make here because you have cos. Alright, because you have cos. Let's consider cos n first. You know cos n is greater than -1, less than +1. Okay, from there you can start the inequality, setting the inequality. You made that already. Now what I would do, I divide the entire inequality by n. I divide -1 by n, then I write cos n over n, 1 over n. Right? Now what I'm doing is I'm getting the limit of the entire statement. So I write limit n goes to infinity -1 over n, and then limit n goes to infinity cos n over n, limit n goes to infinity 1 over n. Alright, so let's consider limit of that. What is the limit of that when n goes to infinity? That will be -1 over 0. This is -1 over infinity, and then keep the middle sequence as it is, and the right side sequence also 1 over infinity. Here 1 over infinity is 0. Then for this you get limit n goes to infinity cos n over n, that is 0. Now you can see the middle part is actually bounded above by 0 and bounded below by 0. Okay, bounded below by 0, bounded above by 0. So the value of this one is also 0 in that case, right? So you have one value greater than this one, which is 0. You have another value smaller than this, which is also 0. So the value of that one should be also 0. So that's how you argue. This is called the squeeze theorem. Alright, so then this says, by the squeeze theorem, you say limit n goes to infinity cos n over n is 0. Okay, that means the series converges. The limit is 0. That means the series which I'm writing right here, cos n over n is convergent. Alright, now let's move to the next example, example number 7. In example number 7, we're going to check this sine square n over n square. You have to check whether this is convergent or divergent. You have to check whether this is convergent. It's lucky because you have sine. You can just set the inequality. You can start from sine. You know sine is always between -1 and 1. And then you square that. If you square this, then you will get sine n between 0 and 1, right? Let's say you have some variable. You have some variable between -1 and +1. If you square that variable, then the value of the square should be between 0 and 1. That you can understand, right? That's very easy. So what I'm saying here is sine n is between -1 and +1, and then sine square n is between 0 and 1. Now you divide the entire equation or entire inequality by n square. So you get this over n square and sine square n over n square, and this is 1 over n square. Alright, now you apply the limit for the entire inequality. You write this as limit n goes to infinity, this is 0. Limit n goes to infinity, sine square over n square. Limit n goes to infinity, 1 over n square. Right, so this will be 0, greater than or equals limit n goes to infinity, sine square n over n square, and this one should be 0. Again, squeeze theorem. Here the lower limit is 0, the upper limit is 0, so the middle thing also be 0. Alright, then by the squeeze theorem, by the squeeze theorem you say limit n goes to infinity, sine square n over n square equals 0. Thus, this series is convergent. Alright, so we discussed 7 problems in today's class. Two of the problem is for the squeeze theorem. 2 of the problems are for the squeeze theorem, and then 2 of the problems are for Hopitals rule. Alright, and then we discuss another 3 problems for the applying rules of the limits. Alright, so that is end of the section. Thank you very much.